Oops. Sorry. Okay, good morning, class. Today I want to talk about light and how light exhibits all of the behaviors listed on the screen. So we've spoken about a variety of wave behaviors over the last few days, and we've spoken about specifically refraction, diffraction. We've spoken about how waves can interfere. We've spoken about the Doppler effect, and we spoke about Young's double slit experiment. And today I just want to highlight how light exhibits all of these behaviors and just discuss that and show how light in many ways exhibits the properties of waves. So let's start with diffraction. And we know diffraction is the process by which a beam of light or any type of wave is spread out as a result of passing through a narrow opening. So here you can see when a water wave comes in, it spreads out, makes these circles as it comes through the opening here. The water wave spreads out. And we experience diffraction with sound waves. If someone's standing out in the hallway, the sound waves that the person is making when they speak, when they pass through the doorway, they will spread out, and we can hear it over here even if we can't see the person. That's an example of sound waves diffracting. Well, we don't see light diffract very easily, but if you take light and you put it through a very narrow slit, a very small opening, we can then see the light spread out. And if you project it on a screen across a room, you would see the light spread out after it passes through a narrow opening. So light exhibits this property of diffraction, this spreading out property, just like water waves do and just like sound waves do. Let's move on to refraction. Refraction is when a wave changes speed and direction when it moves from one material to another. So we can see this light beam refracting when it enters the water. Here we have a light beam in air, and it changes speed and direction when it enters water. And here we have a light beam entering glass, a glass prism, and it changes direction as it enters the glass prism. And here we have a ray of light entering a droplet of water, and you get that prism effect as the light changes direction inside the water molecule or inside the water droplet, and also each different color of light. In white light is comprised of a bunch of different colors. Each of those colors will sort of spread out and change in to a slightly different degree, which is how we get rainbows. But it's not just light that refracts. We can also see water refract. Here we have water waves coming in, and right here the water gets a little bit shallower. And so you see the water waves come in, and then they sort of change direction over here. So you can see water waves do this same thing where they could be moving in one direction, and then they hit a change. In this case, it became shallower, and now the direction adjusts and the wave travels in a slightly different direction. So this changing speed and direction when you enter a new material, or have, in the case of water, a new depth. This is shallow water over here. You see that it changes direction, and also these waves are a little bit closer together, which is an indication that the wave is traveling slower. So we see this refraction effect in both light and water. Reflection is a little bit simpler. We experience reflection every day when we look in a mirror, and that's when a ray of light simply bounces off of a surface. But it's not only light waves that reflect. When we speak, let's say in a canyon, if we shout something, that sound wave goes out and it bounces off of the surface and comes back. We call that an echo. Many dolphins and whales use what's called echolocation or sonar for finding fish and other things. It will send out some sound waves in the water. It will bounce off an object, maybe another fish, and those waves come back, and the dolphin senses that. So we can have sound waves travel and bounce and reflect in air. We can have sound waves bounce off an object in water. And also here we have, it's a little bit subtle, but there's water waves are coming in this direction here, and they're bouncing off this object, and then they are kind of going out in this direction over here. So the water waves come in, they bounce, and they move over in this direction. And here in this picture, what we have is a a person is basically putting this pen in the water and creating these circular water waves that are moving outward. But here, the circular water waves are coming in and they're bouncing against the surface, and you can see the circular water waves bouncing off and moving back out in this direction. Interference is another thing that we've spoken about. So interference, we can see water waves here interfering. Here they build up and support each other. Here they cancel out. And you can see some water waves here overlapping, and they make a bigger wave in certain locations, and they make a slightly smaller wave in other locations where they destructively interfere. And noise canceling headphones here work by taking an incoming sound. The speaker in the headphone generates an opposite sound, which cancels it, and you experience no noise when you put this headphone next to your ear. So we see that interference, destructive interference, works with sound waves, and destructive interference and constructive interference works with water waves. And also, what we saw with yesterday with Thomas Young's double slit experiment was that interference works with light waves as well. And you see this constructive interference where light waves are supporting each other to make a brighter light, and then destructive interference right here when two light waves are canceling each other to form darkness. All right, and last but not least, the Doppler effect. So the Doppler effect, we know, if you remember, that was when the ambulance approached the observer, and you heard one frequency because the waves bunched up. And then when the ambulance passed by, you heard another frequency because the waves were then spreading out when the ambulance was moving away from you. And you can see the same thing in water waves. As this duck is moving forward, the little waves that the duck is producing are getting bunched up in front of the duck. And here you can see a person who is very carefully moving the duck along in the water. And you can see some waves are getting bunched up in front of the duck, and the waves are more spread out behind the duck. So you can see the Doppler effect being demonstrated here in water. But light also exhibits the Doppler effect. When a star is moving towards you, the electromagnetic waves get bunched together and they look more bluish or purplish. When the star is moving away from you, or if you're over here and the star is moving away from you, the electromagnetic waves will be more spread out and it will look more reddish. So all of these phenomenon show that light exhibits wave behaviors just like sound waves exhibit wave behavior and water waves exhibit wave behavior. Okay, so light exhibits all these behaviors of refraction, diffraction, interference. We can see light exhibiting the Doppler effect, and we can see the interference that we saw in Young's double slit experiment. So, in conclusion, this was about as much as we observed until about the year 1900. So, in around the year 1900, scientists believed that light behaved exclusively like a wave. There was no reason for anyone to believe that light behaved anything other than as a wave. And so I just wanted to highlight this. We're going to talk tomorrow about some other properties of light that indicate that it doesn't always act like a wave. But for the moment, I just wanted to highlight that in many, many ways, light does behave like a wave. And we'll pick it up tomorrow with other properties of light that aren't exactly wave properties. Okay, so today's conclusion is in many, many ways, light does behave like a wave and does the things that waves do. Okay, thank you.